Okay, hello. Welcome to another Thinkative Cheeky Half. I'm here with Bill Wimsatt, philosopher of biology, among other things. And as I said before today, we're here at the Philosophy of Howard Stein conference, but the conference is all over now, so we don't have to talk about Howard again. And Bill Wimsatt here, if there was one reason why I decided to do my graduate degree at the University of Chicago, the biggest reason was Bill Wimsatt.
Oh, thank you.
So, Bill, you do a different sort of philosophy from a lot of people, right? So, especially considering philosophy of science. How would you say that the sort of philosophy of science you do is different from, say, what someone like David Malamud does?
Well, David Malamud, that's a contrast that's interesting. He is, in some sense, a very careful analytic philosopher of the exact sciences, where I guess I would be a philosopher of the inexact sciences. But look, there's another deeper and more important difference, which has both David and I and also Howard Stein on the same side with other people. A lot of philosophers look and go out fishing in the sciences for examples to illustrate their philosophical theories. I've always thought we're in the middle of multiple scientific revolutions. I want to go out and see what the scientists are doing and see what from that I can bring back to philosophy. And I've always been interested in complex systems. And in terms of that, particularly since biology and the social sciences end up being the most complex areas, what kinds of features of adaptive systems might be particularly interesting? How can we build simple models of them and not get misled by the simplifications?
Now, when you talk about adaptive systems, I know what you mean by that. But so, for example, living organisms, right?
Yes, exactly.
But not just living organisms. Are there other kinds of adaptive systems that you're interested in?
Well, in a way, Donald Campbell once said, any case of a fit between a system and its environment is a product of selection. So, and Herbert Simon talked about what he called the sciences of the artificial. And by that he meant any system that was a product of a selection process.
Okay.
So I think scientific theories are products of selection processes.
Because we come up with theories, and at some point we choose between them.
We choose between them. We see how well they fit nature. Mm-hmm. Our various aspects of our social structure are adaptive systems. I worked in a design team in an engineering department.
Okay.
And that was, in some sense, an adaptive system. And I got very interested. I also had a background in engineering.
Okay.
And I've always been struck. A lot of philosophers were engineers at one time.
Howard as well, right?
What?
Howard as well.
Howard as well.
And now me.
And now you. And so there's a lot to be learned in engineering about how to solve complex problems and so on. And I was really struck by this. And it's funny, a lot of philosophers, as I said, come from engineering, and they often say, phew, I'm glad I escaped that. And then they go to do philosophy. And then they take off to work on body, mind, or social structures, which are the three great engineered systems we have. The body and the mind engineered in part by nature and in part by culture, by selection, and cultural system partly designed by humans and with unanticipated consequences that may be malfunctional, but in any ways, they're still analyzed within a functional realm.
Well, I've always felt that the faculty at the University of Chicago Department of Philosophy, at least when I was there, had a lot of respect for engineering, and that was partly reflected in the popularity of blue denim shirts that a lot of the professors were wearing when I was there.
Okay.
I kind of thought, because they really respect engineering, they kind of want to look like these blue-collar engineer guys.
That actually came from Richard Lewontin,
okay.
The population biologist I came here to postdoc with, and then I started doing it, and then some other people started doing it. When I came to Chicago, they were wearing three-piece suits and starched white shirts, and I just couldn't take that.
Yeah.
I
miss those days myself, but you know.
Yeah. But anyway, so my attitude, basic attitude is look really closely to the sciences and see what scientists are doing and see what we can get from them. And that means ideally take advanced courses, even an advanced degree, work in the laboratory.
Get your hands dirty.
Get your hands dirty, and also don't be afraid to participate. You're not just a distant observer. You learn part of it by actually getting in there and getting your hands dirty.
Yeah, a lot of it, right?
A lot of it.
What do you call it? Practical knowledge. It's not knowing what, but knowing how.
Right. And something more, I think, aside from knowing what and knowing how, you actually need to know something about why. That is, you have to, to some extent, pick up the values of the scientist and say, look, I'm studying this maybe partly for aesthetic reasons, but also because it's a really interesting organism to use in addressing this question. Okay.
Now, so this is all very much on an abstract level. Now, what are some of your favorite sort of tools of engineering that you've noticed in adaptive systems?
Okay. Well, first of all, my dissertation was on functional organization.
Okay.
So
what's that?
That's an attempt to characterize how parts fit into larger parts and play roles in them, and how they interact, and so on. So it's probably the preferred way of thinking about the organization of organisms or firms or whatever.
Okay, functional parts, sort of like organs in a body.
Right.
Okay.
Exactly. Beautiful. Now, but one of the things I got onto very soon was the idea of robustness.
Robustness.
And robustness, well, I came across it originally in thinking about theory construction. Richard Feynman a physicist, talked about having multiple ways of deriving results. And he didn't want to pare it down to the minimal sort of Euclidean deductive structure. He wanted to keep the messiness and the extra redundancy in, because if one of the results failed, he could always get to one of the inferences failed, he could get to it by another way.
So instead of just having like one proof of a result, you've got lots of different proofs, and then if something changes or something doesn't work, you've got an alternative. You've got a different way to get to it.
Yes, you've got redundancy. And what struck me immediately was that's a deeply biological property.
Redundancy, basically.
Redundancy, and not just redundancy in the sense of identical copies. So we have a liver that probably has 10 times the capacity to deal with it, which is lucky if we drink a lot of beer or get hepatitis. But a lot of ability to repair itself. But also a lot of functional systems have different ways of accomplishing the same thing, not just excess capacity, but so for example, if you look actually at any organism trying to get at something, a rat trying to get at a pellet or whatever, they can use their mouth, their paw, they can push a lever if they've been trained, and so on. So they have multiple ways of doing it, and we have the same. Okay,
so now, but why do you call this robustness?
Because you're able to achieve the goal using a multiplicity of different independent means.
So the goal, or in Feynman's case, the result, is robust because you can attack certain parts, and even if you manage to knock out certain parts of the structure, the result still survives.
Right.
Okay.
Now, also in science, for example, we may have multiple different ways of deriving a result. So it's not just achieving material tasks, but so for example, you could measure a molecular cross section by, say, shooting particles at it and see how many deflected, or you might use a electron microscope and get a high resolution image of it. Or you may put it, if it's an ion, you may put it in an electric field and see how fast it migrates through a gel.
Okay. So lots of different ways to measure the same thing.
Yeah. And now the interesting thing is, each one of them tends to have its biases, situations under which it breaks down or gives the wrong result. But if you've got multiple ways of getting at it, you can often use that to cross-check the other mean and not only tell whether it's right or wrong, but how it's getting right or wrong, and calibrate it.
Right.
So you have this kind of magical thing of being able to take multiple individually unreliable things, and from them both learn more about the acting object and learn more about the means you're using to get to it.
Yeah. This idea of robustness is one of those ideas of yours that I learned from you when I met you in 1993, and which is, they come to mind so often, over and over again. I think, oh, that's robustness. That's what's happening there. And the other one is generative entrenchment, which is a concept that I think everybody should know, and not enough people do.
Well, in a way, that's the complement to robustness. If robustness are the number of ways of getting at something, which are going to use physical detection method, and generative entrenchment are the number of lines of causal effects diverging from something.
Okay.
So
that's pretty abstract. So,
so
give us a basic, what is generative entrenchment for the musical idiot, so to speak?
Well, all right. If you have something like, let's see, suppose you have Newton's laws in a theory.
Okay.
And you use them for everything.
Yeah.
Early on, before they had been as widely applied, they had just a few applications. But as you developed applied science in various ways and mathematical methods in new situations, you generated different variations, say, of F equals ma. So you initially had F equals ma for two bodies moving in a void.
Force equals mass times
Force
acceleration.
Equals mass times acceleration.
Yeah.
But then it was generalized so it could work for systems of particles colliding. And then it was generalized for rotating flywheels.
Okay.
And that's kind of a mind-boggler, because it turns out that the moment of inertia, the amount of force it takes to change a rotating flywheel goes as the fifth power of the dimensions.
Okay.
If what you're doing is talking about the same displacement of it by angle.
Okay. All right. So, but generative entrenchment, I still feel like we haven't quite got down to the basic idea. So let me take a stab at it. Okay. So generative entrenchment to me is where you have, actually in software design terms, we would call it a dependency. It's where you have a dependency that other things are built on top of, so that if that dependency changes, then it breaks everything.
Yeah.
And the stuff that needs to use that deeply entrenched bit of code or whatever or equation or whatever it may be, if that deeply entrenched thing changes, it's just going to break everything. And you see the same thing in biology, right?
Yes, exactly.
So how does that work?
Although it actually can be used as a degree property. That is, you have things that break a lot of things that they break that are lethal, and you have things that break not much, and then you have a whole array of things in between.
So it's a matter of degree, right? There's more entrenched, there's less entrenched.
And now the interesting thing is, the more the danger of breaking something, and because it's deeply entrenched, the more conservative it will be in making changes. Deeply entrenched parts of code you don't want to have to change.
You don't change it, you leave it there.
And
if it works, don't fix it.
Right, exactly. So what you can do is actually, in looking at the evolution of system and the evolution of technology, you can say, all right, how much depends on this? And if it's a lot or a little, you can predict where changes are more likely to be made in the system.
Okay.
So it can actually give you an account of evolutionary processes without ever bringing in genes.
Right. Okay. So because, so if you're looking at, say, a population or a species, then you can sort of predict what kinds of variations you're going to see based on which features are less entrenched.
Yes. Right.
What was the example you gave with the neck bone in the talk today?
Oh, that was some work done by a European developmental biologist a woman named Gallus and her associates. And there's a mutation that changes a cervical vertebra, which are, they have the, no, it changes a, what's the one above the cervical vertebra? Basically a neck vertebra to a cervical vertebra, which has spines coming out of it.
So what are these cervical vertebrae for? Like, why do they have these spines coming out of it?
Well, they have the spines coming out of it because they're going to make the shoulder bones and the ribs.
Okay, right.
So they hook up to the rest of the skeleton.
Right. So these are sort of like little nascent shoulder bone rib bits sticking off the.
Yeah. Well, it's a thoracic vertebra.
Thoracic.
The lowest thoracic vertebra, which is the throat and thorax, changes to a cervical vertebra. You get a couple of these little end spines.
Yeah.
But because in order to do that, what you're doing is modifying the action of the Hox gene. And those are very deep developmental genes. And all hell breaks loose if you do that.
So it's just one gene which determines the shape of this particular vertebra, but also a bunch of other different stuff in the body.
So if you have it happen, then you have a lot of cancers in the embryo. You could be missing a kidney. You could be missing a corpus callosum.
Which is the bit of your brain that holds the two halves together.
The two halves together. And in which, if there's no corpus callosum, you may have two personalities.
Or you may have these weird sort of like perceptual experiences where all this stuff that who is it who did the philosophy paper about the corpus callosum fissures and personal identity? I can't remember now.
Oh well, it all grew out of the work of Roger Sperry, who was a neurophysiologist. But anyway, but the thing is, generative entrenchment also applies to scientific theories. So if you're going to try to modify a scientific theory, try to modify it at as low a level as possible.
Yeah.
Leave the deep stuff alone.
By as low a level, you mean sort of like the outer fringes.
The outer fringes.
Change the fringes, right.
Don't cut the bush at the core.
But then how does it happen that sometimes we find a little detail that we can't quite account for, like, for example, the Michelson-Morley experiments? Yeah. It's just this tiny thing we can't quite get a difference in the velocity of light, no matter which direction it's moving through the supposed ether. And as an ultimate result, we have to go all the way down to the core of the theory and almost start over.
Right. Well, of course, there were attempts to adjust it at lower levels. I mean, at not as deep levels.
Right.
Making assumptions about the ether and so on. But yeah, ultimately it required special relativity to explain it. But it's interesting about that. When you see an anomaly, as Thomas Kuhn said actually, in the Structure of Scientific Revolution, the first reaction is to try to sweep it under the rug. Ignore it. But then,
let's see if we can account for it by just looking at our instruments, or maybe you're being literal. The first impulse is just ignore that one. Let's keep going.
Right. And then if you get more convinced, say, okay, well, let's look at something superficial about the instruments, or maybe a reagent. It's a biological. Maybe a reagent is contaminated, or something like that. And if you look at that, and then that doesn't work, and you have to go deeper. And at a certain point, you say, "Wait a second, this thing is really serious. Let's see if we can study the anomaly really closely and come to understand it better." And so you then do experiments to try to make it more and more robust, make the anomaly robust. That is, you can produce it so it's not being produced as an artifact in the measurement operation.
Right.
And then you try with that. If you can find diverse consequences of the anomaly, try to use those to triangulate on how deep the anomaly is in the theoretical structure and figure out where you need to fix the theory.
Okay.
So,
but I think maybe Einstein didn't really do that. He just sort of took what the anomaly seemed to be telling us and says, anyway, this is the story in my head. It's just a story. But the story is that he sort of takes the apparent result that the speed of light is constant no matter what you do, and adds that with a couple other postulates, and out of just that falls the whole new theory.
Yeah. I don't know that story well enough
Yeah.
to be able to
Right.
respond to
You're a
it.
philosopher of biology, but you talk about physics a lot for a philosopher of biology.
I like physics a lot. No, I did 3 years of engineering physics first, but
Right.
but I haven't continued to study it. Well, actually, we first got together over an interest in chaos,
Right.
which for me was connected with learning modeling and
Okay.
programming on a programmable calculator.
Okay. Oh yeah, programmable calculator. Yeah.
And that was really interesting because I got the calculator. Well, originally I told my wife I needed it for class, which was a lie. But I wanted to play with it. But in fact, what happened was, so I spent, it was just after I got tenured, I spent a third of my year writing every program I could imagine on the calculator.
Yeah.
And writing a simulation manual for my biology course.
Wow.
It was actually the first simulations in an undergraduate course in biology here in '76.
You wrote a simulation manual specifically for like the TI-75 or something like that?
Well, it was for the HP 25.
Oh, okay.
Okay. It was 49 data steps, program steps, and 8 data registers.
Okay.
But it was surprising how much you could do with it. Anyway, so I did this, and I set up a simulation labs. And the more I played with that, I started doing things that nobody had done before and learning modeling. And from that, I developed another professional interest, and that is how you can build simple models of complex phenomena and what you can learn from them, even when you know the model is false. Even when, and I wrote a paper called...
False models as means to truer theories.
Yeah.
Yeah.
And the thing is, many people who don't understand modeling will say, well, that model is so oversimplified, you couldn't possibly learn anything from it. But they don't realize that what the modelers are often doing is saying,
Careful
look,
of the mic right here. The mic's right there.
look, let's look at the predictions of this model, and we know it doesn't fit reality,
Yeah.
but let's see the deviations between the model and reality. And when you then see the form of those deviations, you can say, what do we need to add to the model to get it to fit that?
Okay.
And so it can be a strategy, not guaranteed,
Uh-huh.
to generally add more richer and richer detail to a model and get a better theory.
And now we're back to adaptive systems because
Yeah.
you're taking a model and then you're adapting it to better fit the phenomena that you're trying to model.
Right, exactly.
Okay.
Yeah.
Cool.
And experimental design is in effect that. An experiment is a simplification of nature. Usually you build a lot of control conditions into it so that you factor a lot of the noise that would otherwise come in from other variables out, and you try to simplify the system and learn from it. Now, the other thing, another engineering design principle
Okay.
that's important is modularity.
Okay.
Ideally, you want a theory that you can modify parts of without changing the whole structure of the theory, so that you can make improvements to respond to anomalies without having to reconstruct the whole thing.
Okay.
So it's better if the theory comes in parts, and you can tweak them individually to better tune the apparatus. As a matter of fact, if you think about it, suppose you think about a theory as an integrated circuit
Okay.
that together takes input and then produces a number of outputs.
Okay.
If you couldn't modify parts of it independently and trace the relation between the inputs and outputs, you couldn't localize faults in the theory.
Okay.
You couldn't find where the problem is.
Okay. If there's a problem. Yeah.
And
okay.
that has a lot to do with debugging in software.
Yeah, right, absolutely. And is that related to Herbert Simon's near decomposability?
Yes,
Yeah, okay.
exactly. That's been
Okay.
very important for me.
So it's that things have these dependencies, but there are something like organs which have fewer dependencies on each other than the internal parts of the organs have on each other.
Yes, right.
Okay.
Or else have very controlled interfaces. And that's more like object-oriented programming, or
Okay, yeah.
some kinds of communication molecules for signaling in the organism. That is, if there are standardized interfaces, you can switch one in for another and in a modular sort of way, even if they interact strongly.
You should really just write a software development book. You could be a huge star in the software world. All of these ideas are very, these are, yeah. I mean, in like the day-to-day work of software development, these are all the problems that are being dealt with every day by everybody writing code.
Well, I've always thought that somebody who really knew that area cold could do a better job of it than I could. But the point is, nobody had been looking at it at all.
Yeah.
Well, actually, some people are beginning to. There's an Australian philosopher named Brett Colcott,
okay,
who spent 10 years as a programmer and is now working on issues in evolvability.
Okay.
And doing very nice stuff. And
so evolvability means having a system that's not only designed to have a high fitness to survive in the wild, so to speak,
right,
but also is designed, or so to speak designed,
yeah,
to be able to adapt and change more.
Right, exactly. And it's funny, they call it software maintenance, but it's not really maintenance, it's evolution. Because you say, well, software maintenance is, yeah, I want to be able to put this software on a new system, or I want a new hardware system, or I wanted to have these new applications and so on. And it has to be designed so you can make those additions or changes either in hardware or interacting with the software without reconfiguring the whole thing.
Yeah.
And it's very important to be able to make a new technology or a new organism or whatever using what you've got already. In fact, Stephen Jay Gould, the famous evolutionary and developmental biologist, argued that we evolved largely through a series of co-opted exaptations.
Wait. Okay, so first of all, what's an exaptation?
Okay, an exaptation is something that serves a function that was originally co-opted from something else.
Okay.
You take something that makes something else, and
within an organism, for
within
example.
An organism.
Okay.
And you say, this has a little bit of this effect. If I tweak it this way a little bit, you can get it to do that better. And sometimes the tweak will take off, and its evolution will be driven by that.
I'm trying to think. I've thought of examples before of this, but can you think of an example of like a co-opted sort of?
Yeah, a beautiful one is take the incandescent light bulb.
Okay.
Incandescent light bulbs are, it used to be anyways, the best way of building an incubator for chicken. And because they, unfortunately, they're very inefficient. So about 90% of them comes out as heat, and 10% of the energy comes out as light.
Yeah.
Unfortunately, now we've made progress, and we have LEDs, which put out lots of light and not much heat. So you couldn't use them. And
right. Okay, so the electric light bulb becomes a heater for incubators.
Right. Exactly.
And what about like in the body, something biological where we've seen this sort of like co-opting of maybe a functional.
Well, a very famous example is the so-called swim bladder in some fishes.
Okay.
Which is used to hold air, which by expanding or contracting, it changes their buoyancy.
Okay.
And that, through changes in the gullet, led to some fishes to be able to tolerate getting out in mud where the water ran away, and they could get some oxygen from that.
And here we are now walking around on land, breathing with these things all the time.
Right, exactly.
Okay, cool. Now, lately, I understand you've been thinking mostly about cultural evolution.
Yeah, right.
So what's cultural evolution? What's that all about?
Well, the thing is, we went through a period over the last 2 or 3 million years since we started making tools in which the brain size has increased really substantially. We've gotten taller. We became bipedal. We developed opposable thumb and forefinger and hand control for throwing and for making things and so on. And all of those actually ended up being produced in part by interactions with making tools and using tools and culture. And more recently, there, for example, is there's something that was originally, when it was first discovered by Northern European geneticists, they called it lactose intolerance. And they found that some people couldn't digest lactose after the period of weaning.
Okay.
And then it was discovered that lactose intolerance was actually the common condition. And it was just in Northern Europe that you had this. So they changed the name of the mutation to extended lactose tolerance.
Okay.
And where did that come from? Well, these individuals were herders, and they got milk and made cheeses and things like that. And so they had to use a lot of lactose.
And so then they had a selection pressure for those who could digest the lactose.
Yeah, right, exactly. Culture has increased the number of nearsighted people, because it used to be a bad thing, but now, especially with computers, maybe it helps to be nearsighted. No, it's just that with eyeglasses, we have developed a corrective technology to...
And that then just... so... Sorry, what were you saying about eyeglasses?
Well, the thing is, eyeglasses made it no longer so dysfunctional to be nearsighted.
But we've only had them for a short time, so we're not going to expect any genetic drift with regard to eye.
Well, there probably has been.
Already measurable drift, you think?
Not already measurable selection.
Yeah.
That is, it used to be much worse for you to be, and that's since about 1200 AD.
Okay.
So just 800 years, really.
Right. Okay.
People have learned actually that selection can happen much faster than we've assumed. We have very long generation time, so that's maybe 40 generations. But if we look at other organisms, for example, the measles virus can change substantially and increase in its virulence just as it infects one to another member of the family, because it's adapting to the genes that they share.
Okay.
And on the other hand, cultural evolution can be very slow. So
now let me stop you, because when you talk about cultural evolution, what you're saying now sounds like culture's influence on biological evolution.
Right. Okay.
But there's also this other thing about the way culture itself evolves.
Right. And the eyeglasses is an example.
Okay.
With eyeglasses, you had a selection for developing better and better lenses.
Oh, I see what you're saying.
That led to telescopes and microscopes and
speciation
of optic devices, and to a theory of optics. That is, it became advantageous to have theories of optics.
Right. So theories of optics can be thought of as a kind of organism that thrives in this environment, right? Because
A conceptual organism.
Yeah.
Which, however, has to be reproduced by teaching.
Right.
And so then
you're a reproductive organ.
Yeah, I'm trying to be.
Retired, though.
Well, actually, I'm lucky. I've had 42 dissertation students, so I've had an awful lot of...
Oh, my God.
Yeah.
Right now you have 42 dissertations?
No, I
you
have had.
Okay, yeah, all right.
I've been at it a long time.
So you've been very productive.
Right. Well, and did lots of good feedback, too.
Yeah.
Including people that I didn't... I wasn't actually dissertation chair. I really learned from you about chaos, even though I was already studying it myself. So.
And likewise, and wait till you read Carlotta Verndl's paper. That's that.
I look forward to that. Yeah, and of course, see, now we're exchanging information, and or we might exchange computer programs or papers, or
So these things propagate sort of like genes.
Yeah.
Right. So this was Richard Dawkins' idea, and not just him. There was who were some of the people before Dawkins? Well, let me get the idea out before I ask that question.
Yeah.
So the idea that besides just strands of DNA inside cells being copied and selectively reproduced and mutating, and then the mutation selectively being propagated, so generation and selective retention, right? Besides that happening with DNA...
That's Donald Campbell.
Okay, but it happens also with words, ideas, tools, designs.
Now, where Dawkins went wrong in this, and he went wrong on both of the stuff. There aren't selfish genes. Well, there are special kinds of selfish genes called transposon, but they're the rare case. And there are no really selfish memes either. Then they're not self-reproducing. They require UNA.
Yeah.
And we can exchange words, but I'm not going to be able to teach you to do a partial derivative in calculus unless you've already learned arithmetic, algebra, elementary, intermediate, advanced, analytic geometry and calculus, single variable calculus, maybe a little integral calculus, though not necessarily.
But I have to know some stuff before you can teach me other stuff.
You have to know a whole bunch of stuff.
Yeah.
And my key for the nature of culture and cultural transmission is not, in fact, meme-like thing, but complex sequentially acquired skills.
By the way, just for everyone out there on the internet, this word meme that's so popular now for all those really silly images that get passed around on Facebook, that comes from Richard Dawkins trying to draw out the idea of an analog of the gene that might evolve on its own on a sort of higher platform where we're the platform, and what's evolving is something that's transmitted between us, like ideas or words or dumb pictures of cats with slogans on them. Okay.
Except, of course, Richard Dawkins didn't get either the selfish gene right or the selfish meme right.
Okay.
But that takes complex technical arguments in the case of the selfish gene. In the case of the selfish meme, the very fact that to acquire some memes requires a lot of preparation on your part and a lot of learning means that you've got to take more into account.
Yeah.
And I think the main thing you need to take into account is development.
Okay.
That is, what you're looking at is generative entrenchment and dependency relation in cognitive development and in instruction. If you look at any textbook in the mathematical sciences or genetics or biology or what?
I think we're running out of time.
Oh, are we?
Yeah, because you guys have to get somewhere.